Hello everyone, my name is Chinedu Chukuma and I'm presenting the project titled Design of a High Power Density High Efficiency DC-DC Converter for Data Center Power Systems. The continuous growth in cloud computing, Internet of Things, and advanced artificial intelligence globally has led to the continual growth in data centers infrastructure, which correspondingly results in growing number of servers, networking hardware, and other gadgets. As digital infrastructure demand continues to be improved upon, we see computing keeps growing globally. Data centers are playing a very key important role, and their power supply topology has become an area of interest. And so we see various data center power architectures because as a result of the high demands on power distribution systems to maintain high efficiency and reliability, traditional data center power architecture, which often relies on a 12 volts DC distribution system to supply power to server racks and point of load devices. So, but you find out that at the level of 12 volts, this system have high currents which lead to substantial I squared arrow losses in the power distribution cables and connectors. And so we are trying to look for how to improve upon those losses by increasing the distribution voltage. And that's where hybrid switch capacitor topology comes in, as it significantly enhances the power distribution system by reducing the conduction losses. So we use a 48 volts bus, which has the advantage of simplifying wiring and reducing the number of power supplies required per rack. So that's for our point of load delivery distribution lines. The design objectives. So we aim to design a high power density 48 to 12 volts DC-DC converter for data center power systems. And the aim is also to achieve a high efficiency whereby we reduce the losses by using the hybrid switch capacitor topology. And then we maintain a stable output voltage and evaluate performance. Here's an overview of this work. Data centers are the foundation of the modern digital world. Depending on the type, they support virtually everything from cloud computing to big data analytics, the growth of artificial intelligence. So we see these facilities require a power supply system that ensures continuous operation, reliability, and efficiency. The data center power supply, for that we see there are various stages in the power supply system in a data center, which contribute to the overall goal of reliable power delivery. Fundamentally, data center power system can convert alternating currents from the power grid into direct current, which is required by the equipment, using components like rectifiers and power converters. For the power distribution unit, the hybrid switch capacitor topology is one of the different switch capacitor topologies applied in a power system to provide AC-DC rectification, AC-AC conversions, DC-DC conversions, and DC-AC inversions by integrating the benefits of capacitors, inductors with transistors which act as switches. This topology relies on capacitors and switches, like I said, to control the flow of power instead of heavily relying on inductive components which usually increase the size, weight, and loss in a power converter. The primary attraction to the hybrid switch capacitor topology in various literature is that it delivers a high level of efficiency, a high switching rate, and also power density. Design architecture. Here you can see a block diagram of this project, starting with the DC voltage input, the voltage measurement unit, and then the high frequency switch capacitor circuit to the inductor based buck converter unit, and then our DC output. Design specifications. We use a hybrid approach. The power converter system will have two main stages. The two stages collaborate to carry out pre-regulation and fine-tuning of voltages. The first stage is the high frequency switch capacitor pre-regulator, and the second is the buck converter based on inductors. For the switch capacitor topology, we chose a 2-to-1 switch capacitor voltage divider. The main objective is to drop the input voltage from 48 volts to an intermediate level, about 15 volts or so, by capacitive switching with no inductive components. And so we have MOSFET switches, capacitor banks, and high frequency generators. With a pulse generators, the switching transistor is used to implement the design. And the next stage, which is the inductor base buck converter design, we used a synchronous buck converter to further work on the output from the first stage by lowering the voltage to a constant 12 volts DC voltage. The buck converter has inductors, switching MOSFETs, diodes, and output capacitors. The circuit is to switch the MOSFETs using PWM signals, induce current on through an inductor, and smooth out the output using capacitors. Here we present the assumptions we made in the calculation of the capacitor bank size to provide 4 amps at 24 volts at the output of stage 1, which is a switch capacitor converter. You can see the result here, and also the assumptions for calculating the switch frequency. Also, here are parameters for the buck converter stage, which guided us for our inductor sizing, duty cycle, and the results are presented here. Here's our simulation, which was done in MATLAB Simulink. The system was broken into 2 different blocks. Here is the switch capacitor subsystem, and here is the inductive buck converter subsystem. The individual blocks were tested individually, and then they were connected by connectors. Here we present the results for our simulation. To the left, the 48 volts signal illustrating the constant 48 volts DC supply to the hybrid converter system, and to the right, the capacitance switching signal. Here we used a PWM high frequency in controlling the switching of the capacitor banks. And here to the left is the PWM signal used to switch the gates of the MOSFET of the buck converter, and to the right is the buck converter inductor constant at 24 volts. And here is a comparative plot showing our input and the output of the capacitor switching. In conclusion, the result shows efficient voltage regulation, low profile, as well as high stability in operation. The raw output of 23.7 volts of the capacitor stage was easily adjusted to 24 volts by the buck converter, which validated the performance of the 2-stage design. Also, the topology needs to be further developed as it has great potential to support the future generation of power needs of digital infrastructures. Thank you very much.